my slides. Yes, so I guess I'll start, and thank you everyone for attending this talk, and thank you for organizers for the invitation. My name is Nathan SHAMMAH. I work at the Unitary Fund, and I'm giving a talk about quantum error mitigation with an open source software approach. And here you can find in this first slide my contact details. So feel free to send me an email if you have any question. I will also share it later at the end of the talk. Yeah, of course, today is September, not December. I missed the date. And here are some references about some papers on which this talk is based upon. So yes, let me start. So this is the outline of the talk. First, I'm going to give an introduction to noise in quantum computing, a motivation and overview of quantum error mitigation, and then a more in-depth look about a specific quantum error mitigation technique called zero noise extrapolation. And before providing conclusions for this talk, I will also a bit speak about the Unitary Fund, the non-profit organization for which I work, and the mission we have to promote and support open source software in quantum computing and quantum technologies. So yes, let me start with an introduction first about noise in quantum computing. So so-called NISQ computers, and here NISQ is an acronym referring to noisy intermediate scale quantum computers, remind of the very first computers, classical computers and mainframes. There are very few available worldwide. They're very bulky and they require expert operators. At the same time, they also have some features that those devices did not have, just because we can leverage on an IT infrastructure in information technology that has built up over the past almost 50 years. So they're connected to the cloud. They work with open source software, and they leverage existing user experience and user interface web stacks. So noisy intermediate scale quantum computers are a strange hybrid. And so let me provide a quick look at what it entails running a program on a quantum computer in a very simplified way. I hear someone is someone from the chair saying something. I don't hear very well, or maybe someone needs to mute their mic. Great. So yes, how does it look like to run programs on quantum computers or simulators nowadays? So imagine that you have an hybrid variational quantum algorithm, which entails a classical and quantum part in the program. But let's simplify this even further. Let's just take the quantum part, which in the simplest way, it's provided by the so-called quantum circuit model. And here you can see depicted on the left, there are two qubits. There is a single qubit gate that is applied, and then going to the right, we see that a control NOT gate is applied to both qubits. And of course, we know that quantum circuits need to be more complex to do something interesting. And then, as I mentioned previously, this model of a quantum circuit can be embedded into a relational quantum algorithm in which there is a hybrid approach. There is a quantum circuit, there is some result, and then there is an update with a classical optimization that is obtained. So nowadays, what folks do, if you interacted with available cloud services, from the cloud, you launch this quantum circuit, you launch your job, and you expect the quantum computer to run the job after you're lucky, there is not too long of a queue. And then what you obtain is a series of bit strings. So on the first run, you may obtain a series of 0 and 1s, as I'm showing here. And here, actually, in this example, I'm assuming that the user is launching a quantum program with more qubits than 2, as you see here. And then there is a second run, and basically usually there is a batch of runs because we need to obtain a statistics out of the results that are obtained on a single shot in order to obtain a meaningful result. I see there is a question about a previous talk, so I will continue. So I mentioned briefly this quantum circuit model, and it also has like a very clear mathematical framework beneath. It's not just a sketch, and basically it is based on Schrödinger equation, or in its master equation form, the von Neumann master equation. So here you see rho, which is the density matrix, whose time evolution is provided by this operator k that depends on time applied to rho, and this is a commutator. And so this is assumed to be the noiseless Hamiltonian. The point is that if you apply enough quantum gates to the quantum program, to the quantum circuit in specific, this simple example, at some point, all we will obtain is just noise. It's something that is completely unreliable with respect to whatever execution we applied. And why is that? Exactly because there is noise interacting the system. And this picture, it's an idealized picture in which we're assuming that only the operations that are provided by the user are those that happen and affect the dynamics of the qubits on the chip or in general on the quantum processing unit. But that's not the case. And a way to model what is happening is provided by quantum optics in a very simple way. This is a figure from a paper that studies some properties of quantum optics. Basically, here there is an atom that can be in an excited or a ground state inside a cavity where there is a field. So the atom interacts with the field. And as you can see, this is depicted here with some photon that is absorbed. When it is absorbed, the atom goes into upper state. Then with some decay time provided by gamma, the atom will be de-excited and the photon will be remitted. So this cavity field actually also has some leak that is provided here by this kappa constant. So this is a very simple model that though applies to many quantum processing units because quantum optics is very effective in describing what happens at the qubit level in quantum computers. And another way of seeing the effect of noise is basically that these Rabi oscillations that would happen in this very idealized and simple system, actually after some time are washed out by noise. So the time coherence is very limited. So nowadays in quantum computers, we need to fight noise, and there is two ways to do it: improve the hardware or think of strategies with a provided hardware that try to minimize the impact of noise. That then induces errors in the calculations, and that's basically quantum error mitigation. But let me spend a few more words about noise, because actually the study of noise it's fundamental for the advancement of this field, and actually it's has many aspects to it and has many research involved going on right now. So as I mentioned, there can be decoherence noise, in which we see basically the signal washing out at some point. There can be some control noise that actually is not due to the environment, strictly speaking, but it's due to imperfections in ways in which we are able to translate the operations that we would like to apply on the gate, through a gate on the qubit, with actually what is actually being done. And here you see a block sphere representation in which there is a sigma x rotation. With perfect control, you see the left trajectory, but actually with imperfect control, there is a slightly different trajectory that the qubit undergoes in the block sphere. And this is due to the fact that sometimes there could be some spurious Hamiltonian that is applied when we apply the control Hamiltonian. There also can be pulse-shaped noise. This pulse actually physically can be very different depending on the kind of quantum processing unit one is interacting with. But basically, the main idea again is that there is an ideal Hamiltonian and then there is a noisy Hamiltonian. And then there can also be crosstalk noise due to the fact, as exemplified here with these qubits in a line that may be ions that then somehow interact with each other. We're not completely decoupled, even when we would like them to be decoupled. Of course, we want to couple them when we want to entangle them, but when we're not making any operation with quantum circuit, we would not like them to have any influence on each other. And finally, let me also mention leakage noise. We always speak about qubits, or mostly speak about qubits, but actually there can be quite exotic systems, as the one that has been presented earlier in the previous talk. And more in general, even in superconducting based quantum processors, there can be additional states that are available to the quantum system physically, and this provides some leakage. And here, this is provided by this intermediate state that actually usually is not counted due to the way we're able to tune nonlinearities to just limit the physical space to this 0-1 subspace. But this is something to keep in mind that can always happen. The qubit could leak and dwell into other excited states or states beyond the qubit space. And let me mention already for the first time open source software. Some of you may have attended the summer school of the previous week, in which there was a great tutorial by Alex Pitchford and Simon Cross from the QTIP admin team, also involving this software called QTIP QIP, QIP like quantum information processing, and QTIP like quantum toolbox in Python. And the only thing I just want to mention here, and if you want to know more, there's more information in this publication. This quantum circuit level model can very easily translated into a pulse level noisy quantum circuit model with QTIP. And here on the left, you see this exemplification of a pulse level interaction with many couplings, for example, omega x0, so some x interaction acting on the qubit 0, on the qubit 1, on the qubit 2, and then some z interaction, and then here G1 and G0 refer to some qubit-qubit coupling. So this is something quite unique that can be done by QTIP in a very simple way. There's also other software package at the pulse level. but in Qtip QAP, you're able to simulate and actually design your custom device in a very simple way. Talking about other software packages that have a pulse level description of interaction with the quantum processor. Of course, there is a Qiskit with a Qiskit pulse features, but then there is also like noisy neutral atom based quantum processing unit and simulators, and two of them are Blockade from the QERA startup. Another one is Pulsar from the Pascal startup. And actually, they both simulate what happens when you have an array, or actually a lattice, as you see here in the top right image, of neutral atoms that are your quantum processing unit, that each time can be initialized in an actually specific configuration from a connectivity point of view, thanks to Rydberg atoms properties that can be moved around with and trapped with laser lights, and also made to interact with nearby other neutral atoms. And if you want to know more about open source software enabling the characterization of noise and of these noisy quantum processing units, you can check Unitary Fund YouTube channel, where we record invited speakers providing dive-ins about different software stacks. And so we recorded some tutorials on Qtip QAP, on Pigsty, which is a quite advanced toolbox to characterize gate set tomography, which is a technique to learn actually what are the properties of the gates in the quantum circuit that are being implemented on the real or simulated device with noise, and correct with optimal control techniques what is happening. And then also Pulsar, which I mentioned earlier, which is this toolbox for the design and simulation of pulse sequences on neutral atoms. So, summarizing, noise affects this first part of the talk. Noise affects the ideal quantum computation with errors. Quantum computation is provided by quantum evolution, which entails operations, but also measurement. Quantum noise and classical noise can introduce errors, and different QPUs, quantum processing units, which at the core level have different quantum systems, suffer from different noise sources. So different noise models can be employed, and tools for characterization like Pigsty or Qtip QAP can be implemented to study noise and how it affects quantum computation. And once again here, let me provide this von Neumann master equation. In this case, I'm adding a noise operator, mathematical style L plus a lambda noise scale factor, which is dimensionless. And this, for example, in the simplest form that I can think of, could be a Markovian master equation, in which this part of equation is provided by the quantum circuit, and this part of equation takes care of the noise operator, so all the part that we cannot control directly, and we need to accommodate if we want to improve the results of the quantum computation, also at the software level. So I already started to give a motivation for quantum error mitigation, I hope, with the impact of noise with errors. But now let me get a bit more details about what we mean when we say quantum error mitigation. So many of you may be familiar with a quantum error correction rather than quantum error mitigation. And they are definitely related, but they have some differences. So in this slide, I would like to provide some bullet points summarizing the differences. In quantum error correction, one encodes the logical qubits into many physical qubits. And there are some intermediate measurements for so-called syndrome detection. So there are special algorithms that have been designed playing with symmetries so that one is able to correct the errors basically without looking, but in a sort of an active feedback provided by these special symmetries and special quantum algorithms. So the correction operations are based on the measured syndrome, and so to say they occur live as the main quantum program is running, so to say, as the main quantum circuit, in the most simple way, is still being performed before the final measurement. So there are many studies, theoretical, but also experimental at proof of concept level, that have shown a path to fault tolerance, which means that quantum error correction is scalable, but right now it's still unfeasible with near-term noisy intermediate scale quantum computers, at least with those that are available on the cloud right now. So on the cloud right now, you can access quantum computers in a very simplified way I've shown, but you're not able to implement quantum error correction to obtain an improvement with respect to what you could run without it. Of course, in many labs, there are like exciting demonstration of quantum error correction, being able to provide logical qubits, but still we're not at the level in which quantum error correction is used to make quantum computing impactful on real-world problems. So what can we do right now? Well, there is another approach which now is taking the collective name of quantum error mitigation, which is actually a collection of different techniques coming from different fields, including quantum error correction, which perform multiple and noisy quantum computation to do a sort of sampling, collect the results, and then infer the ideal expectation values from noisy data. So these approaches have generally been shown to be asymptotically unscalable, but at least they're feasible with near-term quantum computers. So right now, as I will show you, you're able to improve the accuracy of a quantum computation that one can run on nowadays quantum computers with quantum error mitigation. And what is even more interesting from my point of view is that these two approaches are not mutually exclusive. This is actually a very interesting paper coming from the IBM team. And here on the bottom, there is a blog post by the same team providing a very clear and easy to approach introduction to the point. In this paper, what they have done, I will not get into the details, but they basically took quantum error mitigation, applied to a part of a quantum error correction protocol, in particular, which involved using some T-gates that have a high overhead, and so they can lead to a lot of errors due to the overhead they introduce. And they approximated the ideal T-gates with quantum error mitigation. So to some extent, they hybridized an ideal quantum error correction technique with into an approximate quantum error correction. So this is also a way to look at quantum error mitigation. It's approximate quantum error correction. So as I mentioned earlier, in the first part of the talk, quantum error mitigation is connected to open quantum systems and noise, quantum error correction. Other things that were briefly mentioned is gate set tomography. This refers to quantum characterization, verification, validation. We also mentioned variational quantum algorithm, and definitely also quantum optimal control. All are fields that are sort of adjacent to quantum error mitigation. And ideas coming from these more well-established fields are informing the state-of-the-art research and upcoming research in quantum error mitigation, which to some extent is a very recent field. So what is the typical workflow to run a program of a quantum computer? I've shown like what happens at the level of bit strings, but let me also here provide a workflow in what happens from a quantum program point of view with a workflow. There is a quantum program we execute on backend, which could be hardware or simulator, and then we collect an expectation value. A small note I need to make is that with all the quantum error mitigation I'm going to refer to, or most of them, we need to apply them with an expectation value. So they're not feasible in so-called one-shot quantum computing usage. So they apply to stuff such as the rational quantum algorithms that are based on estimating expectation values. So in quantum error mitigation, you see the workflow changes a bit. There is we generate multiple programs, which is a way to sample sort of like the variation, the landscape of noise of a quantum computer. We execute on the back end, and then we collect these different measurements, all from these different noisy quantum circuits, and we apply some inference techniques that, to most extent, were completely classical techniques. And then we obtain a single error mitigated expectation value. So now I'm going to provide a very quick, brief overview of existing quantum error mitigation techniques. It's a non-exhaustive overview, so please bear with me if I miss something, but at high level, it's still informative, I think. So the first technique I want to mention is zero noise extrapolation, which is also, I will provide a bit more details about, which is based on the key idea of noise scaling. And I will add a bit more details later on. But basically what you see here, it's again this model of a quantum circuit in which you actually, to some extent here, you're stretching the gates, you're making them longer in time, so more exposed to noise. And so actually you're decreasing the quality of the results you obtain in this program compared to this program, but this actually allows you then to extrapolate to a zero noise value. It's again a way to sample into the noise manifold of the system. There's another very popular technique, which is probabilistic error cancellation, and in general, so-called quasi-probabilistic representations. And they are applied at the gate level value. So here we mentioned our ideal quantum circuit, which you could think of as here, which is a sequence of gates from 1 to t. But actually what happens in on a real device is that we are not really implementing these ideal gates, but we're actually implementing a noisy gate here with some coefficient. So the trick of probabilistic error cancellation is to estimate the ideal gate on the left based on a sampling that occurs in this sort of like linear expansion. Then there are learning-based methods, such as based on Clifford circuits. And basically the idea is to generate training data based on a classical simulator that you see here. And one could say, why should I use a classical simulator to do a quantum computation? At that point, I don't even use a quantum computer to do the calculation. But the trick here is that you can, the quantum program you want to run on the quantum computer is hard to simulate on a classical computer. That's why you want to run it. But you could find a rule to substitute the gates that make the quantum circuit hard with actually Clifford gates. So that becomes a Clifford circuit or a quasi-Clifford circuit. I cannot get into too much details, but basically you can obtain a quantum circuit which is similar to the original quantum circuit, which is hard to simulate, then becomes simple to simulate. And then using these noise models, you can learn how to correct for errors. So basically you define your error correction strategy, again, from an error mitigation point of view, which could be as simple as you see here. It could be like a extrapolation technique, like even just, you know, getting the tracing a line among many data points, and then you use this model to predict how to implement the strategy of the real quantum circuit you want to run, and how to mitigate the result based on the real quantum circuit. Then there are symmetry-based techniques. The symmetry-based techniques are based on ideas that are very similar to the original ideas of quantum error correction, but the difference here is that you do not perform the tricks, so to say, live with active feedback, but again, there is this idea of launching a batch of quantum programs that then are post-selected thanks to these symmetry-based techniques. And here I show here there is an operator M that is applied of the state, and this can be like akin to a stabilizer. The state is not affected by this operator, but we also expect that if there is an error and we apply this operator, as is shown here by the Born rule for obtaining the symmetrized density matrix. Let's say that, as mentioned earlier, we have our state in a Hilbert space that is going beyond the green circle. The green circle represents a set of a logical state, or like of a Hilbert space that we want the system to dwell into. Errors put our state beyond this, and by applying this symmetrized measurement, we project back the state into the symmetrized subspace. So these techniques generally work with making like copies of the state to some extent and running many programs and then collecting the statistics. Finally, the other technique I want to mention is dynamical decoupling and randomized compiling. So when I mentioned that all of these techniques only work when we want to obtain expectation values, actually this does not apply to dynamical decoupling. Dynamical decoupling is a technique that actually works with all ways that we can run a quantum circuit, even when we need to obtain the full density matrix or entanglement properties based on measurement of the final state and not just the expectation value at the end. And the key idea of dynamical decoupling is here on the right. You see that you have a quantum circuit with many qubits, many gates. And here there are inside this square, these rectangles, there are these sequences of XY, XY, or identity XY, XY. So these are sequences of gates that have been introduced thanks to the dynamical decoupling technique and that were not present in the ideal circuit. They don't do anything to the quantum circuit because these are just rotation that then bring you the state back to the original position. But thanks to this approach of keeping the qubits busy with some other operations, you are effectively decoupling them to the noisy environment. And this compilation technique basically avoids to effectively shield from noise. And randomized compiling is a quite similar technique that you see here exemplified on the left. Let's imagine that you start with an ideal quantum circuit here on the left that you want to run. What you actually do is that you apply some gates before and after the gates that you want to apply. And to some extent, this technique is basically they also say twirling. It is changing the noise landscape in a way that is more amenable to correction, so that then one can distill a different quantum circuit which has these different gates. So these techniques apply at the compilation stage. And then there is also other research with a mix of techniques. And this is a slide that you can take a snapshot of in case you are interested into learning more from these references. So as it happens to me always, I understand that I put way too many slides compared to the ones I can show in the talk. So I think I will have to skip most of them. I'm sorry about that, but I will put the slides online for those who wish to have a look at them. And I also point you to this review by Suguru Endu and collaborators on hybrid quantum classical algorithms and quantum error mitigation. So finally, yes, I need to skip some slides, I'm sorry. But basically, maybe what I can say here about this slide is that how could you use quantum error mitigation, and in particular MITIC, which is this open source software that we develop at Unitary Fund? Well, you have a problem of interest, such as quantum simulation, for example, the quantum field theory. You compile it into a quantum circuit, for example, through totalization. Then you choose the best hardware with a specific fit, and then you run on hardware with quantum error mitigation. So what we think will happen soon, and to some extent is already happening, is that notwithstanding what application you have in mind for running your quantum circuit on a real device or a simulator, adding a layer of quantum error mitigation is fundamental to benchmark what you can obtain and then compare with the state of the art. And of course, if you publish open source the code and the supporting data, this helps the field to advance faster. So here I'm showing this paper by other researchers in which actually they improved the simulation, the quantum simulation, by applying a mix of zero noise extrapolation and readout error mitigation, which are techniques that now you can use in MITIC, this Python toolkit that is open source, developed by Unitary Fund, that you can use online. So I already mentioned how we run quantum programs on the cloud. I just want to say that right now you have a bunch of front ends, cloud services, and backend providers, and you could go like through the expected way of using, you know, the front end that is the same of a cloud service, and then on some of the most referenced quantum processing units, or you could use one of the other quantum processing units they provide with some other features, but then you could also use some other front end. And so right now there is a patchwork of things that one needs to take into account when running these quantum programs. And in order to run these quantum error mitigation techniques, one needs to have low-level compile control that sometimes is applied behind the scenes by cloud services disabled. So yeah, unfortunately, I don't have time to give too much of an in-depth look into zero noise extrapolation because I think that my time is up. Let me just mention that MITIC is this. I also asked the chair if that's correct. I think that my time is up right now. Is that correct?
Omololu, how much time does Nathan have? Okay, you keep talking. Eventually, Omololu will let you know. Okay, go ahead.
Okay, great. I will just mention that MITIC is this Python toolkit for error mitigation. It is compatible with most of these front ends, as I was listing them earlier: Cirq, Qiskit, Bracket, you name it, Penny Lane, even the OpenCASM standard. And then it's designed to be backend independent. So it is a collection of all these techniques for zero noise extrapolation, probabilistic error cancellation, and many more, digital dynamical decoupling, readout error mitigation, and more are being added. And basically, they all are applied at the gate level. So that is what makes it backend independent. And this is the white paper that has been recently published in Quantum. And I encourage you to go online at mythic.readerdocs.org to have a look, or check the paper on Quantum or the archive to learn more. I need to skip all these slides, unfortunately. It's a lot of research being done. I want to say only two things, 2 minutes. I'll take 2 minutes to start, to finish. The focus of this talk was Mythic. I also want to mention that Unitary Fund, as a non-profit, is also involved into financing research and open source software in Quantum. So we give out these micro grants that have no strings attached. They're $4,000. Anyone in the world can apply. We've given grants to 22 countries. They led to 16 publications and over 30 libraries. And Metric is just another product that we support for benchmarking. You encourage to go at metric.info to check it out. Again, more than 50 teams have received these micro grants. Please go to unitary.fund/grants. If you have an idea, a project through which you would like to be supported, and you will be paired with mentors if your project is accepted, that can also help you advance on your project. One of the first projects that have been given out actually was from a student from the Congo studying in India. He designed a quantum programming language, and now he's a quantum engineer at Zapata Computing, a quantum software startup, and he's actually a Unitary Fund advisory board member. Right now, we have a grant that is being completed on quantum convolution neural networks from a student from South Africa. And so this is just an example of the fact that we're also interacting with Quantum Africa nowadays. You can find more information online on our YouTube channel from interviews from winners. And let me just close with this slide. Right now, we're running a quantum open source software survey at Unitary Fund, and the survey closes soon. And we would be delighted to get your answers and on what you think the stack needs to add, the quantum software stack, what you use, and what's actually the best way to make this community more inclusive and more diverse. So please follow these links to fill out this survey. So this is the last slide of my talk, and I thank you for your time.
Oh, thank you very much for a great talk, Nathan. Fantastic. Let me see here. There is a talk in the chat, a question in the chat saying, thanks for your nice presentation. Please share the PPT at the end of the presentation. I don't know if it is available, some version of it in the Unitary Fund.
Yeah, I will definitely share it. Yeah, no problem.
And then essentially, if you want, you can, so people can go to the Unitary Fund website, and then there will be a link, something to PowerPoint presentation or something like this, no?
Yes, exactly. I can also share the PPT with the organizers. So that's perfectly doable. Oh, actually, let me share here also in the chat.
In the chat is saying, like, regarding the survey links, if you put the survey links in the chat box.
Oh yeah.
Because there are two chat boxes, one with the panelists and then another one with the other. So therefore the director of the center might be able to cut and paste and put in the other Zoom channel. Mm-hmm. Okay, great. So therefore, people who click on the chat on Zoom can actually find the survey for open source software, I thought there were two links. One is
Oh
open.
yeah, but if you click to this one, then you will find also the other one at the end. So
okay. So therefore, and it takes like 5 minutes to fill out or less. So then regarding the back of your slide, it says programming languages. It marks Python. So that means that the other languages are not supported. It's only Python hardcore.
No, I was. This is just a big of a joke because it's like again a background we made for the survey, and I'm showing that I selected the Python as a programming language that I use most, and that's the reason. Actually, here is a QR code. If you want to take a snapshot with your phone, you're also able to get to the survey. Thank you all. And I don't know if there's any question. And sorry for being a couple of minutes over time, but I guess I also started a couple of minutes later.
Are there additional questions from the audience that regarding now the emphasis in the future is going to be more like on Mythic, or like there is some other plan in a different direction, or what's the next step the unitary fund is going to look like in the future? Like
yeah, definitely using Mythic to improve quantum computation. Actually, we're doing a field study about it, and there's more users using it to improve what is possible without error mitigation. So that's the plan. It's adding more techniques, also like fixing bugs and adding more features to existing techniques. There's also like a question by Honorine Nonfin. Thank you. As you're able to run some quantum program, I would like to know if the quantum computers are already available. If not, where are you setting the software that you use for running? Okay, I will answer via script. So then the next speaker can. I will type the answer so the next speaker can start with the presentation.
Yes. Okay.
Actually, now we have a break. Coffee break. We'll be back at 11:30. So we have a break for 20 minutes and be back at 11:30. Yeah. So Nathan, you can answer the question, and then we'll be back at 11:30.
There is a break, so you can go ahead, and Nathan.
Okay, great. So what I will say is that if I understand the question correctly, is like what software you use to run the quantum programs, and that's a great question. There is, as I mentioned, many software available right now. For example, Qiskit from IBM, Circ from Google, many front ends. And then there are cloud services that you need to connect to be able to run the software. So in specific, Mythic is able to run on all of these. But I also wrote a blog post that I'm gonna share here in the chat, which is how to run programs on quantum computers for free. Because an issue definitely of these devices is that they may require credits or money to be able to access them, but there's also ways to get some of these credits for free, and so have some QPU access for free. For example, IBM has a bunch of devices that are available for free on the IBM Quantum, and here I provide more details. I give some indications for how to run for free. I will also answer live to Chunyu Chen, and I will say that his question is, do we need to characterize the noise before performing the quantum error mitigation skill? That's a great question, and generally it helps, but it's not required. It depends on the technique. So for example, zero noise extrapolation based on these technique that makes the noise higher and then extrapolate to zero level just by adding gates to the quantum circuit does not require a knowledge of a noise model. But of course, the more you know about the noise model, the better it is, because, for example, if you know that noise affects a specific kind of quantum gates, you may use this information to scale your quantum circuit. And also when you apply the inference technique, you may take this into account, having an exponential model for decay, for example, of coherence in place. For other techniques, such as probabilistic error cancellation, you need to make a noise characterization. So definitely, as you mentioned, these two parts of error mitigation are important, which is error characterization, noise characterization, and error mitigation.